this is identical to classical mechanics. You know, this is physics 1 stuff. The total energy is the sum of the kinetic and the potential energy, like for a pendulum or a stretch of a vibrating molecule or something like that. Absolutely. Now, in the classical world, let me kind of go down here. In the classical world, we could probably write E equals a kinetic energy, if we have one particle, 1/2 times the mass of that particle times its speed squared, that's little v, plus the potential energy, that's classical. Quantum mechanical, we'd say, hey, the energy equals this, but I'm going to write it as this kinetic energy term is p squared over 2m plus v. Now, a little reminder, lowercase p here equals linear momentum and the linear momentum is mv. So if you do p squared over 2m, substituting in mv here, you're going to get m squared v squared over 2m, which is going to be equal to 1/2 mv squared, if you use that classical definition. But as you might well expect, we've got a different approach to doing this, okay? And let's see what we've got. So I'm going to kind of render this in a quantum sense. We're going to say, we're going to let P be a linear momentum operator. So P equals minus I h bar d dx. Okay. Now you might ask, where did this guy get this? Where did this crazy, ridiculous, stupid thing come from? Well, let's look at this. I got a little bit ahead of myself. Now, you always want to remember de Broglie because he was born on my birthday, August 15th. So, now do you remember what this guy did?
I have no idea.
They
I'm
they talk
excited.
about it a little bit in general chemistry, sometimes, depending on the course. The idea that particles have wave-like behavior, and waves have particle-like behavior. So there are instances when electromagnetic radiation, light, behaves wave-like, like radio and TV or cell phone signals, very wave-like. But there are cases where a light behaves very much particle-like. There's like particles come in and collide and move things around. They come in like bullets and shoot things. So you've really said, waves and particles, there's kind of a sloppiness that sometimes light or electrons act more like particles, sometimes they act more like waves. That's called the famous wave-particle duality. Okay, so de Broglie says, wait a minute, we're getting this wave-particle duality, and then Professor Schrödinger, and you know what else he was doing while he was doing this. Maybe he had mattress waves that were inspiring him. All sorts of oscillations. Okay. I can't believe I said that. Okay. Schrödinger developed a mathematical description of these so-called matter waves, or small particles like electrons around a proton, like atomic hydrogen, right? And his mathematical description, by the way, was in terms of differential equations. So de Broglie said, hey, there's wave, that small scale matter is wave-like. Schrödinger said if there's waves, then they obey a wave equation. Okay? And a wave equation can have both a kinetic energy and a potential energy components. Okay. So, and the kinetic energy would be a T component, the potential energy a V component. Okay, so de Broglie is saying, hey, wave. Schrödinger is saying I can set that to mathematics in the form of a wave equation. And the mathematics stems from the total energy being the sum of the kinetic energy term and the potential energy term. If I'm going to do things quantum mechanics wise, and I'm going to look at wave behavior, I still have E equals P squared over 2m plus V, but I want to start thinking about waves in terms of kinetic energy. Okay? Now, let's do some intuition. If you're on a rowboat in the ocean, and the waves are like that, that's okay. But what if you're in a storm, the waves are like that? Okay? And they have steep crests and steep troughs, and they're coming at you really fast. That's a lot of energy in the waves. If you have a very low amplitude and a low frequency, there's not energy in the waves. So low amplitude, low frequency, low energy, and high amplitude, high frequency, high energy. Okay? So we're kind of good with that. So one way to assess the energy of a wave-like system is to ask for the curvature of the wave, or the momentum of the wave to ask for the slope of the wave. If you have a perfectly flat, still ocean, there's no momentum and there's no energy. But if you have a storm and the waves are going up like this and down like that, you have high curvature and therefore high energy. Okay? And so these were the ideas that, isn't this cool stuff? This is kind of neat. It's weird, but it's neat. So Schrödinger said, hey, we've got to get at something that models this being this and this being this. It has to do with the slope and curvature of the waves. Okay? So the linear momentum is somehow related to the first derivative with respect to position of the wave. And convince yourself that the energy is the correct. Momentum is kilogram meter per second. This dx is a meter in the denominator. And h bar, we won't worry about per cycle per photon. We'll just call this a joule second. And so,
that's 1 kilogram per meter per second, right?
Right, so this is a kilogram meter squared per second squared times a second, and divided by a meter, and convince yourself that all those units break down to kilogram meter per second. By the way, I think it's enormously helpful when you do calculus and physical chemistry that you evaluate the units. Kilogram meter per second, joule seconds, kilogram meter per second squared divided by meters. We drop the meter squared down to meters, or seconds down to seconds. We have a meter, and everything just works out really nicely. And those truly are angular momentum, or linear momentum units.
What's I?
I is the square root of -1.
Okay.
So that's the complex. So I, by definition, equals the square root of -1.
The imaginary number?
As the imaginary number I. Now, there's an interesting reason why the I is appearing. It turns out that you can't see the waves themselves. You can only see the amplitudes or the square of the waves. And you can kind of see where I'm going. This is P, and this is P squared over 2m. And so if I take this linear momentum operator, so I'm working on curvature of the waves. I'm saying all the wave behavior we want for quantum mechanics is built up in the curvature of the waves. Well, if I substitute this momentum term, God, it just seems like a second ago and we're almost out of class. So this has got to be it today, okay? So we are going to substitute that in for linear momentum here, and I actually put it in the wrong place, into P squared over 2m, the kinetic energy term. So T equals P squared over 2m, but if I have this curvature slope deal going, and I put that in, this is minus h bar squared over 2m d squared dx squared. Now, convince yourself of that. What's minus I times minus I?
I. Or
Well,
one.
I minus times a minus is 1.
Yeah.
And I times I is minus 1, so that's where I get that minus sign right there. The h bar is squared, and we interpret squared saying you apply this derivative twice. And a second derivative is a curvature in the strict calculus statement of what a second derivative is. Okay? The first derivative is a slope. The second derivative is a curvature. And what this isn't in your book, by the way. This is directly from me, PhD quantum mechanics, okay? What this says is that the kinetic energy of small particles like electrons going around hydrogen nuclei, the kinetic energy is related to the curvature of the matter wave. High curvature, high energy, okay? So if you want to rip a 1s electron out of a uranium atom with a plus 92 nucleus, I guarantee you that 1s electron is in a high energy, high curvature quantum orbit, if you will, okay? This is curvature. This will get us at the curvature of the matter wave. And at this point, let's look at the whole thing. We've got 4 minutes to do so. So what we do is we define a new function h called the Hamiltonian. Or the total energy operator. We'll see why I'm calling things operator in just a minute. The Hamiltonian equals the sum of the kinetic and the potential energy operators. So this looks a lot like what I had over here. I had E equals T plus V in the classical world. Now I have this total energy operator equaling a kinetic energy operator plus a potential energy operator. Okay? So H for one particle is minus h bar, little h bar squared, or 2 times the mass of the particle, d squared dx squared, plus the potential. Okay? Now, can we get any further? We have to introduce